My name is Joshua Melugin, and today I'm going to talk about the states of matter using this simulation. This simulation comes from the University of Colorado. This simulation has three different parts, as can be seen in these three different tabs at the top of the screen. In this first window, you can adjust the temperature of these four different atoms and molecules and see the effect that it has on them. You can also change states by clicking on these three different buttons. Second window, you can do this basically the same as the first window, but this one you can also see pressure, and you can also adjust the volume of the container and introduce more molecules into it, so atoms or molecules into the system. This third window plots potential energy versus distance between atoms and creates what is known as a potential energy well. And I'll begin by talking about this. So for neon, we can see that the potential energy well is relatively shallow, and we can observe the distance here, and then we can compare it to argon, and we see that argon has a greater distance between atoms, and we also see that the potential energy well between argon atoms, or the potential energy well for argon is much deeper than the potential energy well for neon. And what this means is that argon has a higher affinity for argon than neon does for neon, as can be seen by the differences. And what we can also do is we can adjust atom diameter. And what we see when we adjust atom diameter is that this largely just affects the distance between where the minimum of the potential energy is, not the actual minimum of the potential energy. But if we adjust the interaction strength, we see that this changes the depth or attractive forces between two atoms or molecules. So the stronger the interaction, the deeper the well, which means the harder it is to pull these atoms, or the more energy it takes to pull two atoms apart. So using this logic, and we compare neon and argon, we can note the differences here. Since argon has a deeper well, we would expect that it's harder to pull apart, meaning that it would take more energy, meaning that the system would need to be heated more than neon. So we'll move to this first window to try and see if this is true. So for neon, we'll see that the liquid phase for neon is about minus 247 degrees centigrade. Now when we switch to argon, we would expect its temperature and its liquid phase to be higher, and it is indeed by like about 50 degrees, 60 degrees centigrade. And this is what we expected. So this shows that affinity, or an atom or molecule with a higher affinity, takes more energy to be put into to swap from the solid phase into the liquid phase. And it takes even more energy to get it from the liquid phase into the gas phase, as can be seen by the large gap between neon and argon. You can also note the differences between O2 and water. Then we'll move on to this window, and we can do the same comparison between neon and argon. And we can see that, right? You can see this little red dot at the same phase, or the same number of liquid and gas phase for neon. It requires argon to be heated to a much higher temperature to achieve the same equilibrium. And this last little bit, we can adjust the interaction strength between these atoms or molecules in here by sliding this bar. And what we see is that as we decrease interaction strength, the pressure will increase, which indicates that more and more and more of the atoms or molecules are entering the liquid and then subsequently the gas phase. So what this means is that the interaction potential or the potential well of atoms or molecules greatly influences what state of matter or what phase of matter the atom or molecule is going to be in. The greater the depth of the potential energy well, the higher affinity an atom or molecule will have for each other, meaning that it will take more energy to separate these two. The inverse is also true. This has been a simulation on the states of matter.